Hello, good morning. This is Paul Barua of the IEACCC Call Centre. Welcome to the March webinar. I'm an author and actually, am I an author and analyst at the IEACCC? Yeah, I suppose. Yeah, I'm going to introduce myself. Ask the top people to know what he is. Yeah, okay, fine. Our monthly webinars are based on technical reports which are available on our websites. Residents of member countries and employees of sponsoring organisations can download the reports free of charge after a one-off registration. And please visit our websites for details. The subject for today's webinar is retrofitting lignite plants to improve efficiency and performance. And this will be presented by Mr. Ian Reid. He's one of our fellow authors. The report on this topic has been out in draft and will be published in the next couple of weeks. If you have any questions during the talk, please use the Ask a Question box at the top of your screen, add your email address so that we can send you a fuller answer if we run out of time during the question period. Now, I shall now hand you over to the speaker for today, Mr. Ian Reid. Thank you.
Hello, and thank you for joining us for the webinar today. This is Ian Reid, and I'm an author at the IEACCC Call Centre. Today's presentation is on lignite plants improving efficiency and performance, and it's really aimed at existing plants that need to improve emissions treatment, but perhaps cannot implement the major expense of selective catalytic reduction and flue gas desulfurization. There are three parts to the presentation. One is on performance efficiency, another is on emissions reduction, and the third theme will be on the flexibility of plants to cope with alternative energy sources. The first slide is looking at the broad scope of lignite power around the world. And in fact, there are over 1,000 stations, and of those, about 700 are over 100 megawatt capacity. Over the last 50 years, the maximum capacity has been rising, and this reflects optimum scale for steam turbines around 600 megawatts. In the last 10 years, the plants have introduced ultra supercritical and supercritical steam systems into lignite power, but the majority of stations remain as subcritical stations, and that affects the efficiency of plants. In the future, we're still seeing construction of lignite plants. There's a new ultra supercritical plant being installed in Thailand, and around 600 megawatts capacity, while in Laos there's an 1800 megawatt plant that's introducing subcritical technology. So that really affects the carbon profile for that plant for the next 20 years. And the other theme that's happening is that some stations in Western countries, such as Germany, are being reassigned as reserve capacity stations in response to renewable energy. Looking at the challenges facing the industry, this gives an impression of what has to be done to operate in today's environment. In the USA, the introduction of the Clean Power Plan is not only involve lower emissions from lignite power stations, but also is seeking improvements in the heat rate of plants, which is particularly difficult when introducing emissions technology reduces efficiency. And the added factor there is the competition from cheap natural gas. In Europe, the main challenges are from renewable energy, where for the first time we are seeing lignite power stations that normally act as baseload power having to be withdrawn from the system. In China and India, there's a significant response to severe pollution in these countries. India is introducing new legislation on emissions for the first time. And in China, smaller plants with high emission profiles are being closed in preference for large, efficient units. In the overall scheme, the carbon dioxide has exceeded 400 ppm for the first time, and that's reflected in these new carbon dioxide targets, which reflect on the emission of plants. Well, NOx and SOx and mercury and particulates are all seeing much tighter limits in the future. So how can we respond to these challenges? And these are the three themes I want to look at today. On efficiency, clearly the largest effect would be to introduce ultra-supercritical steam systems, but that is very unlikely to happen in older plants. And so we're looking to improve the feed quality for efficiency. Where the low energy content of lignite is a substantial challenge to the industry. And we're also looking to introduce new technology and upgrade parts of the plant, including steam turbines, to improve efficiency. On emissions, the selective catalytic reduction and flue gas desulfurization are the preferred technologies for new plants, but for older facilities looking for lower cost investments and perhaps at the expense of operating cost, there are a number of technologies that may be combined in hybrid systems or are addressing more than one component that would be of particular interest to plants that are struggling to meet the latest regulations. I would also like to say a little bit about the carbon sequestration project at Boundary Dam, which has implemented CO2 recovery on a subcritical plant. For flexibility, the demands of the inroads of renewable energy into the power generation mix means that for the first time, lignite plants may have to move out of base load operation and into more variable operation. And there are a number of strategies that could be adopted to address that. And these include energy storage, varied demand response, sliding pressure control, and also cogeneration with natural gas where appropriate. This slide's too busy. If we not to go into too much detail on this slide, but this shows where a number of the energy losses are found in a lignite power plant, and covers the heat load from water content in the fuel through to decaying heat transfer systems, decaying steam turbines, the inefficiency of fans and pumps around the system. Now, overall, the biggest impact on efficiency would be to use higher severity steam systems, but that's not really open to us for these retrofit plants. And so at the bottom of this slide are some of the reported improvements from implementing efficiency upgrades. And the best of these are really around beneficiation of the lignite and updating the steam turbine, which is actually a very popular upgrade for lignite power plants at the moment. I have to think about that slide. Oh, it's stuck. Right. If we just take a look at lignite feed quality, if we look at this slide shows the water content on the vertical axis and ash content on the horizontal axis. If we look at the blue section, which is the German lignite, we see that's a very high water containing fuel, and that's driven the research efforts in Germany to eliminate much of that water to improve the energy content, which is shown in these diagonal lines across the slide. So as we move down in water, the energy content rises, and also as we move from right to left across the slide, as we reduce ash content. The purple section is the lookout from the Czech Republic. You can see it's particularly challenging, as it's both high ash and high water. And the quality of these fuels, to some extent, dictates the technology that's been adopted, as subcritical systems are much easier to operate with high ash fuels. If we look at some technologies now for improving the feed, I'm left and right-handed here. I've selected these two technologies to talk about, as normally high energy streams are required to dry lignite prior to emitting the fuel to the boiler. But there's great interest in using waste or low energy streams to dry the lignite prior to emission, and that way the energy that was lost in boiling water is now transferred through the system to electricity generation. The first system here is from RWE, the WTA dryer, and it uses a low pressure steam to dry lignite at around 110 centigrade, and can remove vast amounts of water from the fuel. The DryFining system, which is in the primarily aimed at the American market, where water content of lignite is lower, removes less water but contains a beneficiation stage which removes mineral matter from the fuel, and that means that less pollutants and ash are passed through the boiler and have to be removed later in the system. And overall, by implementing these types of systems, we can expect efficiency improvements of between 1 and 2%. Although in a dedicated plant designed specifically for dry lignite, the improvement could be much greater. Yeah. Looking swiftly to steam turbine upgrades, this slide shows how the pattern for deterioration of a steam turbine over time. Each of the zigzag profiles of the rise in heat rate is due to maintenance and repairs at 5-year cycles. And this is a typical plot for turbines that would have been installed in the 1990s, so perhaps typical of the turbines existing in most of the older plants. And as you can see, there's a substantial deterioration in the turbine over 25 years, and some turbines are much older than that. There have been a number of advances with new higher efficiency three-dimensional blade technology, and also with new materials to resist the impact of particles and corrosion and creep on the turbine. And altogether, these improvements can lead to substantial benefits in performance. In fact, I've seen 14% efficiency improvements from upgrading from a very poorly performing steam turbine to a new one. And the latest developments are that the new steam turbines can be installed in the original casings from other manufacturers, so that can really reduce the downtime needed to install a new turbine. I need two right hands. If we now turn to emissions control technologies, the focus has been to find technologies or combinations of technologies that can compete with an SCR. An SCR is a substantial piece of equipment and to install a full-scale SCR on an existing plant would require substantial downtime and be very costly. But there are a number of options that may be of interest to that can match the performance of an SCR unit. The base technology to consider is the selective non-catalytic reduction technology, and that has improved substantially when combined with low NOx burners, and can now be installed on larger plants. The previous limitations around penetration of the reagent into larger boilers is be overcome by using urea instead of ammonia in many cases. And careful temperature mapping of the boiler means that the injection of reagent can be done much more efficiently. So it's possible to get down to around 200 milligrams per meter cubed with an NCR system, which of course isn't as good as SCR, but could be the basis for adding another technology on top of this one. In this slide, I'm showing an SCR system, but it's not a full-scale one. This is a compact SCR. It's about a quarter of the scale and can be installed into the pipework at the exit of the economizer without having to do foundations and so on. And it could be installed in a fairly short outage. The advantage of this system was originally conceived as a ammonia slip trap for an SNCR system, but actually combining the low NOx burners, the SNCR, and the compact SCR can compete very well with a SCR system. The only concern for Lignite would be the high ash levels, and it may be that we'd have to be positioned after a hot ESP, but certainly an option. Normally, all the technologies for NOx reduction involve addition of ammonia or to reduce the nitrogen oxide to nitrogen gas. An alternative is to oxidize the nitrogen oxide. And in this technology, which is based on ozonation, first of all, we still need a low NOx burner. We would need the SNCR technology, but then upstream of wet flue gas desulfurization unit, we can inject ozone into the effluent, and that reacts to form dinitrogen pentoxide, which is a soluble product and converts to acetic acid in water. And that can be very effective at removing NO. In fact, depending on the energy input, the NO could be almost eliminated. The reason I've combined it with SNCR is that going from 200 to 100 ppm would require about 1% of the plant power output. So it's much better as a refining technology for NO. Oh God, I meant to say something. There are two more technologies I would like to talk about that involve NO, but as these are multi-component technologies, I'll just say a little bit about sulfur oxides first. And the removal of SOx is dominated by wet and semi-dry FGD systems, virtually 100%. So to bring new technology in to compete with that is very difficult. But in fact, there are a number of technologies that are of great interest. Just looking at the options first, the dry sorbent injection technology is probably the cheapest to install, but it is the least efficient in use of lime or trona So perhaps you might use 4 times as much reagent as in a flue gas desulfurization unit. But the low capital cost could make that an attractive technology for a retrofit. And in fact, a plant in Oklahoma has just installed that. Spray dry and circulating fluidized bed scrubbers are also an option. They had been limited in scale, but can extend to 300 or 400 megawatt scale now. And although they use somewhat more lime than wet flue gas FGD unit, the lower investment cost may make that attractive. And we've already talked about improving the fuel to remove sulfur at source before admitting it to the plant, which is attractive. But there are 2 additional technologies called Airborne and clean combustion, and I'd like to say a little bit more about those. One is using sodium bicarbonate reagent, which reacts with both SOx and NOx, while the other system adds a new add-on gasifier onto a boiler and eliminates downstream equipment. So both are quite new. Airborne is actually being implemented to achieve very low NOx and SOx emissions, and the clean combustion system is currently running on an old stoker furnace in the United States. So if we look at the Airborne technology first, this slide shows the treatment side of the system, and in fact, these are actual data from plant operations, and there is an SCR catalyst in place. So the NOx coming to the Airborne system is around 100 milligrams per meter cubed. The sulfur dioxide hasn't been removed. The effluent passes through a baghouse to remove particulates, and then sodium bicarbonate is added to the effluent. And on the right at the top, we can see the emissions resulting from that treatment, from that reaction, and very low emissions are achieved. The problem with sodium bicarbonate in the past has been it's quite expensive to produce, and the new feature of the Airborne technology is the recycling of the reagent. So ammonium bicarbonate is used to regenerate sodium bicarbonate with the ammonium nitrates and sulfates reclaimed as fertilizer products, and that substantially improves the economics for this process. Okay. I'm enjoying the practice. Yes, the clean coal gasifier. On this picture, there are 2 parts to the reactor. The right-hand part is the original boiler. Am I running out of time? No. Okay. I've run out. The original boiler is on the right-hand side, and on the left-hand side is a new gasifier reactor that would be added on. The way it would be done is to drill ports into the water wall of the boiler to add the gasifier. The gasifier is complete with around 4 burners each, and within the gasifier there are fuel-rich conditions that form syngas, carbon monoxide, and hydrogen, but also convert fuel nitrogen to nitrogen gas. So this eliminates the fuel nitrogen source of NO. Also, in this reactor, lime is co-fed with the fuel, and it's intimately mixed with the fuel and converts the sulfur to sulfide is removed as slag. So there's much less solids material passing into the original boiler, which remains much cleaner. And on the right-hand side, the boiler is now a staged air combustor, where the combustion is completed, but with some energy removed from the stream, limiting the formation of thermal NOx. So without any additional treatment equipment, the emissions of SOx and NOx can be around the 100 ppm mark. Flexible, I've got a fair bit yet.
So do you just want to skip to the last one?
Yeah. I've got flexible, and I've got one example. Yeah. Then I've got carbon mitigation, and I have concluding remarks. Yeah. So, yeah, I'll stop there.
Okay.
Yeah.
Okay. So.
Yeah, because I have to think about what I have to go say. Yeah. Yeah. Pass on. Yeah, and so thank you very much for listening to this presentation. You too. and I'll pass back to Paul.
Questions?
If you scroll down, no, I'm sorry, up, I mean, then there's the questions.
Great. Well, thank you very much, Ian, for that fascinating talk. The PowerPoint will be available to download from the webinar page of our website. Oh, it's downloadable, is it? Yeah. It's just viewable. Oh, brilliant. Didn't realise that. The next webinar from the IEA Clinical Centre will be presented by Toby Lockwood in April, on the last Wednesday of April, and he'll be talking about next generation carbon capture technologies for coal. What we'll do now is we'll just now wait some questions from the audience, and Ian will answer those as best he can. If not, please leave your email address, and if you'd like a detailed answer, or if you think of questions later, please don't hesitate to get in contact with us. Thank you. Okay, well, thank you very much for your questions. As I said, Toby Lockwood will be presenting next month, in the last Wednesday. And thank you so much for listening, wherever you are, and goodbye.